Okay, sorry about that for all you who are joining on the recording. We're just at the lecture objectives for our lecture today, lecture 28. So that's kind of what we want to cover. Before we dive in, I just thought I'd pause for a moment, see if anybody has any questions on any outstanding stuff. Okay, and let's see, I think I will repost I think we have pretty much everybody now. I'll repost the links file again in case that didn't come through for folks who joined a little bit later. 1 second while I do that, and then we'll be on our way. 28 links, functions, there we go, okay. And so even though I call this functions 1, we're gonna have 2 lectures on functions today, and then on Tuesday, probably take all the lecture on Tuesday, but we might pull in some new stuff there. But basically, this is kind of advanced function topics, which is interesting and fun. So this is basically the topics, and we'll extend it a little bit on Tuesday. All right, so let's get going then. Quick stuff. So obvious and easy. No one should be confused about this at all. So basically, you know, we know about function prototypes. We know that when we follow something with a semicolon, it's just a prototype. It's kind of a forward declaration. It's letting the compiler know that sooner or later that implementation is coming and that we can thereafter kind of implement the guts of it inside the braces that explains what the function is going to do for us. The first prototype just gives us the semantics or the function signature. We also saw way back function overloading, where we could change the function signature but use the same function name, which allowed us to address different ways in which we want to call the function. Not just on the number of arguments, but maybe the type of arguments, or whether they are references or constants. So restating the function with these you know, same guts maybe, or similar implementation, but you know, different function signature is a way to just make our functions a little more usable by the rest of the world. And then the one caveat just to remember is we can't overload simply by changing the return type. That was something we said we cannot do, right? And so I just put that there for references. For reference, I think that's something we looked at quite a while ago. But that hopefully is all pretty familiar to you. That's stuff we've seen before. And then of course, default arguments, and these all go for constructors as well, and methods in a class. So I know you guys know this stuff, but there it is one last time just to remind you, okay? And then to just contrast with what we're going to talk about, quoting, you know, quotes inline with these lambdas, just so you remember what inline as a keyword is. Inline was kind of an old style compiler keyword that will tell the compiler, hey, I just want you to copy the guts of my implementation wherever you see the word inline. So if I said inline void print line, it's going to request that the compiler replace the print line hi there with the actual code that implements that call, right? So it takes up more room in memory, but it executes in theory faster because it's not putting something on the stack and calling the function stack that we usually do to kind of change execution to jump into a function, right? It's just actually gets put there by the compiler, almost like templates a little bit, right? So that's what inline is, and that's a little different than what we're going to see today with this thing called lambdas. But you'll see that the usage of it is got some similarities. And then the last thing I just wanted to touch on again, since I know we didn't spend a ton of time on this, at least not on functions, is just hope that you remember that you can templatize any function, right? So if we have a function of type, you know, returns type Q, and maybe its arguments are also of type Q, and we warn the compiler that this upcoming function is going to be a template, we can then call the function, of course, by putting the type inside of those braces, or inside of the less than and greater than sign. And that's effectively what the compiler does. And it does it at compile time. It lays out any usage of get max with a different type inside of these less than or greater than signs over there is going to really just tell the compiler, hey, please make me one of these before we go to our runtime context, okay? And we saw that, of course, with classes. We won't go into that. But so that's the other kind of way that we can do something interesting with functions. And we saw that much earlier. So now, before I threw this in at the last minute, because I promised you guys I would put this out here. And my goal with this is not to terrorize anybody, but to give you all another option if you want one. If you had a bad homework and you just want to take a crack at replacing that one grade, you can do that. Now, if you don't do this, it's fine. It'll just be as if you never did the 10th homework. But what I like to do, and I'll put some more detail around this in Canvas, but I wanted to put it out there now so you can think about it if this suits you, is you can do just, make your own board game, right? So pick a board game, doesn't matter what it is, as long as it's a board game and it's turn-based. And then, I'm going to put this all in more clearer writing, but the general notion is follow the pattern that we've been following. Implement your game within a class. I would like to see you use inheritance in this in some way. It can be super trivial, like generic game derives into the game that you're creating, just so I know that you remember what inheritance looks like. And then have some kind of a board game with pieces. No AI required, and I ask that you try to follow our best practices. In other words, don't regress back into, using 2D arrays when we could use containers, that kind of thing. And then if you can implement a virtual method, great. That's great through inheritance. So that was our last topic. We'll give you 15 points bonus on that. So it kind of gives you sort of an opportunity to raise the bar even higher on the grade that you're replacing. So that's a general idea. I've just put some suggestions for games out there. You, of course, can make up one that's totally new as long as I can understand what you're trying to do. But I wanted to give you guys a chance. I know there's not a lot of time left. Don't feel like you have to do it, but if you do, you have an opportunity to kind of raise your homework score a little bit. So, and this is only for the homework, just to be super clear. So the best you can get on your homework is 100% out of all of them. So I'll have to cap that off if you exceed it, but that's the general goal. Any questions on that? Okay, cool. I know I just kind of chucked it out there, but I wanted to get it on in their minds before things get completely crazy, so that if you did really need to replace a homework, that this would let you have a shot at that. Okay. And what I'm hoping is it just gives you some creative freedom, so you can kind of just have fun with something rather than trying to follow all my .h files, which I know you've been doing most of the semester. Okay. So that's 10, optional. We'll swap out the lowest grade for that grade, okay? Okay, so with that, let's talk about functors. Functors are a thing that transcend multiple languages, and I'll sort of try to state the problem that they're trying to solve for us, but they solve a lot of different kind of problems. But hopefully this description, explains at least one case, right? So imagine that we have just two functions, inc1 and inc2, and their respective jobs is to increment a variable by either 1 or by 2, right? So that's kind of two very similar functions. Obviously, we really have no business writing two functions that do something so similar, right? We would never want to write 10 functions for 10 possible increments. This seems terribly silly. What we would have thought to do, most obviously, would be to pass in n, which is the amount we want to increment a by. So now we've got a more general function, which is really nice, and useful. But as we're going to see today, in a lot of situations, and we saw this with our thread example, when we create a thread, we pass in the name of our worker function. And then we have this issue of, okay, well, gosh, that function needs arguments. So how do we tell doit that when it calls our worker function, we need to pass in all those extra arguments, right? So what we did and what we saw with threads is, we would just kind of tag on those arguments after the name of the function, right? So if I wanted to do it to call increment to increment v, here I want do it to call increment to increment v, but I'm going to tell it as an extra argument, how many it should increment by. It's okay to do it that way, right? It's just a little clunky. You start getting confused about, well, what are the arguments that go with inc that are going to be passed to inc by doit, and what are the arguments that doit's using? It just doesn't seem very object oriented, right? So what can we do to solve that problem? That's really what the functor does for us. And it's really more of a strategy for design and object-oriented design than a formal syntax that's specific to C++. Any language that has class-based object-oriented syntax or semantics can actually implement this functor idea. So I put it in here specifically because it is one of these many concepts we've talked about that you will see again if you go to other languages. You'll see this concept represented. Once we describe it, you'll understand what it is. So it's not a reserved word. It's not a specific syntax that is a functor. It's just the way we're going to actually create and overload a class so that it essentially acts for us like a function. So the idea is we're going to create an instance. We're going to instantiate the function, right? We have a class that's sort of a rubber stamp for a function that we may or may not create. And we can create many instances of that function. And each instance that we create of that function might be slightly different than the other functions. So how would we go about doing that, right? Well, the key thing is we need to overload the parenthesis operator, the function operator. So two parentheses together like that, we've seen overloads for plus and minus and divide. So if we create a class where we overload the parentheses operator, we're basically saying, oh, you can say the name of your instance of the class and follow with some parentheses, and I'll assume you want to call this overload operator. That's what I'll assume you're trying to do. Much in the same way if we put a star after the name of an instance where we've overloaded the multiply operator, then it would think, oh, you're calling the multiplication overload. So this is a new overload we haven't really seen before. And so with that, we can create this notion of functional objects, an instance of a class that acts like a function when I use the name of the instance. So the name of the instance becomes the actual name of the function that I want to call, right? So let's take a look at some examples. So this is an increment class. Now remember, the class here is just the rubber stamp. We haven't created the function yet. We have to instance the class to create a function. But we're going to have our increment class have a inc private member. And this is going to be the amount by which we want to increment some value every time we call the increment function, right? So, so here's our constructor, and this is the constructor for the function, right? So think of increment as a rubber stamp that's going to create 1,000 different functions, and each one is going to have a different increment that it's going to use whenever incrementing a variable. So our constructor is creating the function. It's not incrementing any values. It's just actually creating the function, if you will. And then here's our overload operator. So we're overloading the parentheses, and this is the key bit that turns an instance of this class effectively into a function. It could be many other things too, but we're just going to implement this one thing that's going to allow us to treat it like a function. So when we say, oh, okay, well, when you call this instance as a function and you pass in some number, an integer, and I've called my integer argument val to inc, this is the value we want to increment, and I'll come back to why we have a const here in a second. Then I just return the val to inc plus whatever this particular instance of the function was created to do. If it's supposed to increment by 1,000, then we'll be incrementing val to inc by 1,000. But if some other instance of this class was constructed with an inc of -1, then that particular instance of the increment function is going to actually decrement. You know, it'll be incrementing by -1 or decrementing by 1. So that's it, right? That's all we really need to kind of create this concept of functors. So let me pause there and see if anybody has any questions on the concept. Okay, I'm counting in my head to 5 now. I've decided I need to wait, wait 5 seconds. I think I was probably going too fast in the past. But of course, always interrupt me if you have to at any time, right? So key points to remember though, we're not, the class does not constitute the function. It's the rubber stamp by which we, almost like a factory, we're going to crank out functions, right? And then each instance is a different flavor of that increment class, a different flavor of that increment function. So let's try this. We'll do a real simple example of this. So we're going to create a decrement class, or have you modify a decrement class, right? And then have you write the overload for that operator, and then decrement the value that's passed in by 1. Now, you just need to think about calling the instance in main like a function. It seems really strange to call the instance of a class like a function, but once you do, this is the operator of your class that's going to get called, right? So you'll create an instance of the decrement class. You'll initialize some separate integer variable to 12, right? And your decrement class, your constructor will have no arguments. We're just going to decrement by 1. So we're going to have a really simple functor here. It's just going to only ever decrement by 1, right? You'll have some other variable set to 12, and then you'll call the instance of your decrement class like a function and pass it in a value and assign the return of that to your original value, right? And you'll see this in the code when you click into it. Some of you might have already jumped into that. And then just go ahead and print out the returned value, right? This original value, print it back out again so you can see if it actually got decremented, okay? So that's pretty straightforward. Make sure that it changed, right? And then think about if we wanted to have it actually literally change the argument that we passed into the function of our functor, how would we do that? You can probably guess because we've done this in the past, but since this is a whole new context, it might be a little confusing to you. So let's give that a try. That link is in the link file. It should be your first link, I think. So take a look at that. I'm going to repost one more time the link file just in case not everybody got it. And you guys jump into that and we'll take a couple minutes. Interrupt me if you have any questions. 1 second. Put that link file up one more time. There we go. Posting. Okay, there you go. Okay. All right. So I'm going to give you about 2 minutes on that. Hit me with questions. Maybe I will roll the screen back too, in case anybody has any questions about the syntax there, because I realize all the syntax is kind of new. So bear with me, I'll go back so you can kind of see how that was implemented on that previous screen, okay? Okay, let's take a look at that. All right, so simple functor class, decrement class, right? So here's our class, and we have everything public because that's really all we need to do. And we don't have to have a constructor on this one. Seems a little strange, but since we're not really passing in any arguments to decrement, which makes decrement kind of not a super useful function, because once we create it, all of our versions of decrement are going to be exactly the same. So this we've started super simple. But we just have this overload on the function overload, and we're going to pass in a value, and here we'll make it const, and I'll explain that in just a moment. Essentially, what that allows us to do is pass in a 12 or a 2 rather than the name of a variable, and then we can return that value -1, right? So we're just returning, we're not modifying the argument that was passed into us in this case because it's constant, right? But we could have also overloaded that operator and done it yet again and said, okay, I'm also, in addition to wanting to be able to decrement a constant value like a 12 or a 2, I'd also like to be able to decrement a non-constant value. And in fact, I would actually even like to be able to modify that value in addition to returning the decremented value, right? So in this case, and this wasn't specifically called out, but if you wanted to do that, you pre-decrement val here, right? So we're being a little fancy. We're going to pre-decrement val, which is going to modify this argument that is passed by reference. And then it's going to return that result, right? So we accomplished 2 things in one line here. So that's just another way we could do this. And that allows us in main to actually invoke that call in 2 different ways. If you noticed, if any of you looked at the solution, you see in main, we can not only say, call our instance name with an individual integer, we can actually, or constant integer, we could pass in the variable as well and have it change. So that's kind of, oh, there we go. Yeah, I got the code on this page, right? So our final answer equals D12. That works through our constant overload, right? And then we could also do something like this. We could say D original value and ignore the return value here, right? Remember, D is an instance of the decrement class, right? Its constructor, it created the function. The overload allows us to pass in the 12, okay? Any questions on that concept or the syntax there? Cool. Yeah, hopefully you guys get this. We've done a lot with classes, so pretty straightforward, although a new operator that we're overloading there, but relatively straightforward, okay? And you might ask, why would you want to do these things? Well, one is you might want to customize these functions like we said. 2, sometimes it's just nice to not instantiate a function until and if you need it. So you can imagine a library that has 1,000 functions, right? And you load that library but you don't really need to use maybe more than 3 of them, right? So this kind of approach where you instantiate the function when and only when you need it could be a more optimal way to invoke functions out of a very large library. There are other examples as well, but this is just one or two reasons to consider a functor. Okay, so that's functors. It's an idea, it's a concept. This is going to be on the final. I'll remind you of this. We'll have some practice on functors, and I think maybe even a Quizlet for you. But it's an object-oriented way to create a functional object, right? That's fairly customizable. Okay. So now let's look at the next thing, which is an important tool in our function toolbox, function pointers. We've made reference to this in the past. Functions are pointers, can be pointers. And so we've actually passed functions often in the past in the semester as arguments to functions. We said just put the name of the function in, like with our thread constructor. We just pass in the name of the worker function. We didn't put the parentheses there because we don't want to call it. We want the thread constructor to call the function. Well, what does the thread constructor signature look like? Well, it's got to have some syntax that describes what a function pointer looks like, right? So, so we're going to actually look at how you would do that. So here, I guess my key point here is really at the end of the day, a function is just a kind of address. It's a slightly special address. It's not a pointer. It's actually known to be a function, right? But we can force the name of a function. If we really wanted to, we could use this thing called reinterpret cast. We could cast a doit function to a void star and print it out. And instead of calling the function, we would actually be able to visually see the address of the function. So if we left all this stuff off of that call, we would actually end up, invoking the function, or it would say, wait a minute, I don't know what you want to do with that. But this is how we actually can do that. What is a pointer of type void? It's a strange beast, actually. I'm not sure I can do that justice with an explanation, but you can, it's a way of casting a pointer into an arbitrary type that's not going to be interpreted any other way, I guess. It is one way. I brought it up here just to get around what cout is trying to do, because cout's trying to interpret pointers all the time and decide whether they're characters or strings or whatever. But there are a number of different weird applications for void stars. Okay, so to reference to that thread constructor, right? We could, we would like to know how to do what the thread constructor does, right? We want to be able to declare an argument in our function so we can receive a pointer and use it in some generic way. Because as we have seen in some algorithm library functions, we can actually pass functions in all the time. So maybe we would like to write some cool functions like that too. And so that's what this slide is all about, right? So how are we going to go ahead and create that? So here's the basic type. So when I want to create a function pointer, right, I'm going to have a return type. And then I have this strange syntax here that is a little intimidating when you first look at it. But I have these parentheses. I have the name of the function inside of the parentheses and a star. And that specific syntax is letting us know we're declaring that func name is a pointer, is a function rather, a pointer to a function that has a certain return type. And it could potentially have arguments as well. So here's some examples. Int myfunc of a is a pointer to a function. So myfunc of a is a generic variable that can hold a pointer to a function that returns an int, okay? So we're not creating a function here, we're creating a variable that can hold the address of a function that exactly matches this type. No arguments and a return value of int. So this is the function signature of this myfunc pointer, right? Similarly, if I wanted to have a double, if I wanted to have a myfunc b pointer that points to a double, I could only hold the address of functions that return double values with no arguments. I would create myfunc b like this, okay? Now let's say this is just a contrast. Myfunc c has one argument of type int and it returns int. So any kinds of functions like that could have their values stored in myfunc c, and so on, right? So just as we've seen, there's all sorts of sensitivity to the way that we pass arguments. Are they const? Are they not const? All those variations and the return values go into the function signature. So these pointers have to be declared to match the function signature of the addresses they're going to hold of other functions. And we're going to do an exercise on this to help drive that home. So syntax aside, does that idea register? Does anybody have any questions about that? The idea is this is a variable name, just like an int or a char, but in this case, it can hold the address of a function, okay? Everybody good with that? Oh, parse types, a semantic way to parse types. You mean like, oh, I have an address, what kind of type is it? Is that the question? There, we'll see that we can kind of operate on these types, these pointer types, but there are, oh, yeah, yes, yeah, there, I'm trying to remember what it is. I don't remember off the top of my head what that is. And then I got to check. And often, and I apologize, as I probably mentioned once or twice, I keep switching languages in the middle of the weekend. So I always hedge a little bit because I can't remember the specific syntax. But I believe there is something in C++ that will allow us to do that. But I will have to check on that and get back to you. Good question. Good question. And a useful one, right? Obviously, a lot of times you need to know that. Often, though, in C++ is not quite as common as in JavaScript or Python. You know, those languages, when they have, you know, interpreted types, the types are kind of fungible and often you don't know. C++ is so locked down that it's generally not object oriented and or could design to consider having a sort of fluid type situations. So I'm pretty sure it's possible, but it's not very common, I think. So let's go ahead and just do a couple quick tests. So I have, this is an integer, okay? And you will have some of these on the quiz. So this is why I'm, and on the final probably, I think, because I don't think this is on quiz 6, but you'll have an opportunity to practice these. But that's an integer, of course. That is a pointer to an integer. It is not an integer, it's a pointer to an integer, right? That is also a pointer to an integer. You might not know it, but those parentheses in that case don't do anything for us. It looks suspiciously like a function pointer, but it's not. It's just got some extra parentheses in there that don't do anything. That, however, is a function pointer. And the only difference, as you can see there, is we've added the extra pair of parentheses as if we were saying, hey, this is going to be a function with arguments. That's where most people get lost. That is not a function pointer, that is, okay? It's a very strange syntax. You know, if you try to memorize this, it's a bit rough. But if you kind of think about these two differences, that's how I remember it. It's like, okay, well, that's nothing really other than that. But now we've changed things. That's a function pointer, okay? So we've declared val to be a variable that holds the address of a function that returns an integer and has no arguments, okay? And there's a slightly different kind of function. You know, obviously I couldn't have everything called val, and this wouldn't all be in the same line of code or in the same program. These are just individually considered, right? So that would be a function that returns a pointer to or a function pointer that returns an integer and has these two arguments, okay? So those are the two that actually are function pointer declarations. All right. Any questions on that? Oh wait, let me see. I think I might see one. Oh right, no, I think we've covered that or tried to. Okay, so how do we go about assigning these? This is where things get interesting. So imagine that we have two functions, a walk function and a run function. Let's think they do something maybe in a game to make a character walk or run, right? And the input to those functions are the same. They have the same function signature, but they're going to do something different internally. One's going to move quickly and one's going to move slowly. And in this case, we're just sort of printing out a debug message to represent the work that the function's doing. But you know, the idea is the guts of these functions are fundamentally different. They have the same function signature, right? So what's the value of that? Well, now we can actually have one pointer that holds that, right? So we'll say my func int. That's really also the same function signature as we see up above, right? Returns a void, has an integer argument passed in. And we don't need to name our argument here. We just need to give it the type. So my func is a generic pointer that could point to either one of these functions that we've created. So I can manually just assign my func to run, right? And then I can go ahead and invoke my func just like I would be calling run. I pass in a 10 and it'll just do the work. And if we're working in a scenario with a bunch of these that have the same function signature, I don't even really need to know, you know, which function I'm calling. You know, maybe it was decided by some other process. I just need to know I need to call it now. This is very much what's happening inside of these functions like the thread constructor. When we pass in our worker function, that thread constructor says, okay, well, you gave me a function. I'm just going to call it with the following arguments that you sent to me. Okay. So that's what we're doing now. We're actually getting into the mechanics of creating that for ourselves. Okay. So that's, you know, a small example, right? So we're going to do an exercise next, and this slide will kind of set that up. So we're going to, you know, pull together a few concepts. We're going to take a map, key value pairs. Hopefully everybody remembers that. So the key for us is going to be a character that is going to represent, you know, which function I want to call, right? So think of a game where you're jumping or crouching or running or, you know, whatever, or shooting. And we have one letter characters that represent each of those actions in the game. So that's our key value of our map, right? and the key in the map. The value is, okay, what function is associated with that action, right? So as a game designer, you might say, okay, well, I'm going to set up this map with key value pairs, and I'm going to register all of the keyboard characters that are associated with a particular game character action, run, jump, fight, whatever. And then the function that's going to get called is going to be this function right here as the value component of the map. So now we have this lookup array of functions, right? Generic functions that presumably, let's say for the moment, all have the same function signature, right? So this is our container type, our value there, and the name of our container. All familiar stuff. The only new piece is this piece right here, right? That syntax for our function pointer. That's our value, okay? Okay, so this is what we're going to do in our exercise. We have an animation table, and this is not too far away from real world, at least for 2D games anyway. So we're going to create a map of animation function pointers. It's just like we saw on the previous slide, and I'll unwind so you can see that for reference. And then we're going to create a little interactive game, as simple as it is, where you're just going to type in input, get a character, just like you're kind of doing with your maze game that's coming up. And then you'll use that character to look up in the map and invoke the associated function call, right? You'll call that function number. Oh, and the other thing is, we're going to, addition from getting a character for which thing we want to do, we're going to input a number that indicates how long we're going to do it for, right? So we've just kind of made it very simple, right? And then you're going to use that character to look up the right function, and you're going to pass it the integer that comes from you, the player, okay? And then you'll just repeat that. You'll just keep going and going and going until you type in an X and then break out of the loop. So now I've written most of this for you. And so take a look at that. Let's see if we can do it. At least you'll get to actually see this in practice working. I'll set the timer here for about 3 minutes, and we'll sort of take most of that and see if anybody has any questions. And then I'll glance over the code too and just sort of narrate any kind of gotchas that I see there. Okay, and just let me know if you have any questions. I'll keep an eye on the chat as well. Oh, and I'll roll back here so you can see the syntax as well. Give me 1 second. So I think this part is done for you, but I think maybe the most useful one will be to leave you on this slide here, maybe. Yeah, I'll leave you on that one for now. And then I'll take a look at the code now. There we go. Okay, yeah, so just a little narration for you. You guys have seen this and figured it out, but the A table in our practice here is just our map. It's our lookup table, right? So you're just really going to be calling that function directly out of the A table. And of course, don't forget to enter a number for your seconds. If you get it working, you'll need to do both of those things. Enter a character and a number. Okay, well, let's take a look at the code for that while people are wrapping up. Pretty straightforward stuff, but just want to let everybody have a chance to play with it. So there's our, of course, there's our variable, right? Looks like a function, but we're just declaring a variable animate, which is a function pointer variable, right? And then we just go ahead and set it to that, just for fun. We're just testing it, but animate equals run. We can do that, not a problem. We could also then call animate directly with 10 and it would run for 10 seconds. That's just to remind you of that syntax. There's our A table, right? And the value portion of it is again, just describing the type of the pointer. We've seen maps of pointers, right? We looked at maps of shared pointers. We looked at maps of pointers. So this is just another kind of pointer. It's a function pointer. So that's not really that new. So here's setting up our table. We do that manually, right? And then our loop to collect the command. That's just to break out, get the time that we want to do that action for. And then we just invoke it, right? Straight from the A table. We say A table of command, right? And then we put the parentheses out there and pass in the time. And that's kind of crazy, but also quite powerful, right? The fact that we can call functions like that, we can build function tables and look them up based on a key, or maybe some computational challenge that is not known until runtime, right? Maybe you have multiple solvers for some physics problem, and based on the scale of the problem, you might invoke a different solver, and you want to have a big lookup table that you can look up based on some value, right? Like there's any number of ways you can take advantage of that kind of capability. So that's pretty cool. Questions on that? Okay. So those are function pointers, right? And there are some things that, there are some challenges here, right? Like in this particular example, we would not want to just look up, some bogus character. It's good to check and make sure that that didn't exist. We wouldn't want to accidentally create a value of a null function pointer. So we have to be smart about how we use the map. And then also in this particular example, all of our functions obviously have to have the same number of variables, or at least defaults, right? So that we can actually drop out a few of the variables and call them in slightly different ways. So, so that's in the way that we're doing this. That's one of the risks or the design considerations we have to keep in mind. Okay. Okay, so those are function pointers, right? So we've seen functors, which are classes or instances of classes that can be treated like objects, or sorry, treated like functions, because we overload the function parameters, right? And then we looked at function pointers themselves and how we can actually store those in variables, which is a slightly different syntax, but something powerful we can do with functions. And now we're going to look at lambdas. So lambdas are another one of those concepts that transcend languages, and they're kind of all the rage these days. It seems like a lot of languages are essentially implementing effectively what a lambda looks like semantically and kind of what it does for you. So a lambda is a very lightweight transient function that comes and goes in the middle of your code. You don't have to declare it somewhere else or put it in a separate file or have a prototype. It's just like, hey, I need a function. I'm going to create one right here. I'm going to use it, and then maybe it's going to go away, or I'm not even going to think about it anymore because it took up so little code that it really doesn't matter. So that's what lambdas do for us. And under the surface, they're basically functors. The compiler, when we implement the syntax we're going to look at here in a second, the compiler is implementing them as functors, this idea that we saw with classes. But it's doing it magically for us, so we don't have to worry about it. And the syntax is pretty concise. So these are small inline, in quote, functions. You'll see what I mean by that in a second. They generally perform some small task. They're pretty efficient when we use them, and especially when we combine them with stuff from the algorithm library. This is something we will do a number of exercises on just to drive this point home. We'll look at the for each function from the algorithm library. There's also an accumulate function. I think we saw these earlier. There's a whole bunch of these that you could design your own or implement your own lambdas with, but we're going to look in particular at the for each today. Okay. And as I mentioned, the lambda is just translated into a functor by the compiler magically behind the scenes. And it's a lot less, tiresome, because once you know the syntax, they're really, really quick to write. They don't have a type, right? A lambda isn't a specific type. And you'll see that as such, when we need to declare them off to the side, we need to use the auto keyword. Which is a little strange. It's kind of a perversion of the auto keyword, but auto is the keyword they chose to allow us to sort of create one of these standalone lambdas. So we'll see a couple examples of that. But also when we use them directly in an expression like the argument of the function, we don't have to use auto at all. We just kind of write the function right there in the argument. We'll do that. And the result of the function feeds the argument of the other function that's wrapped around it. So we'll do a couple of those, or at least one of those. Unfortunately, the only drawback right now is lambdas can't be templated, which is probably you guys would be thankful for in this class, because that's just a whole lot of syntax that you'd have to digest. And as we'll see here, lambda syntax is a little bit intimidating when you first see it, but we'll try to break it down for you as simple as possible. So it looks kind of like a function. We're going to break it down one piece at a time. But basically, auto, as we said, if we're going to create a lambda, and if we're going to give it a name, right? And we don't have to do that. We would do this inside of main, right? That's the key difference with lambdas, is we're doing them kind of on the fly. So they don't need to be declared outside of main. We could do it inside of another function or inside of main. So we'd say auto f equals, and f might be my decrement function. And we'll describe what this capture clause means. But these would be the parameters of the function, and this arrow means the type that we're going to return, right? And here's our implementation on the inside of this, okay? So that's the basic structure of a lambda. So I'll kind of go through this one bit at a time here, and then we'll do a little bit of the coding on it. If you have a question, just jump in, chat to me, or just jump in the microphone, because I know this is like a lot of syntax. But so let's break this down. So the name, right? So here's the name of our lambda, right? So auto is the type that we use whenever we're naming a lambda, so that we can invoke it like a function. So I'm going to name this lambda f, right? And then that is going to allow me to call it later on, right? So even though these things are pretty transient, I can give them a name, and I can, be in a particular area of my code inside of main or some other function and use them for a while. And then when the function goes away that contains this lambda, the lambda goes away too. But this is how I would do that, right? And we have to use the auto if we're going to give it a name, right? So later on we could say f, and then whatever these parameters would be up here, I can just pass it into the f, right? And that's going to call my lambda. Just like if it was a function or a functor, we really at this point don't even know the difference, right? For the most part, it's really pretty much the same. It's pretty interesting. I haven't quite figured out how I make my pointer bigger, but it seems to happen sometimes. Okay, so let's talk about the capture part of that. So that was the name. So what is the capture? So capture is a very strange beast. But if you think about our functor example, if you think about at the beginning of the lecture, I said, geez, wouldn't it be great to have an increment functor that we create an instance of, and one of them increments by 10, another one increments by 1,000, right? So that we did in the constructor of the functor. Well, the capture clause is really very similar to the constructor. You can think of it as the constructor for the functor. We're passing in some parameters that we want the functor to lock into its definition, so that it can just have access to that information, right? So if I was making an increment by 10, I might pass in the number 10 here, and then I'd say, if I had some other parameters, I'd pass them in, but increment was a pretty simple function. We would just probably only pass in the variable that we want to increment, right? And then I can optionally have the return type on there if I need to, which we'll talk about in a minute, okay? So that's our capture clause, right? And it essentially identifies any variables you want to feed to the definition of the lambda. We're not calling the lambda here, right? We're just defining the lambda. That's really important, because capture clauses are confusing. You think, okay, wait, are these the are these the arguments to the function? What are these things, and why do I need them? Because I have arguments to the function here, and I also have this capture clause. This is the constructor for the function. Later on, we're going to call it with parameters, but when we create the lambda, we're going to pass in these values right here, okay? So it allows us to basically collect or capture local variables, if you will, that exist in the scope when we're defining the lambda itself. It captures those local variables. You can think of it that way. And so they just kind of are available to your implementation of the function in here, just like we said with our functor. And you can also pass them by reference. This is the crazy thing, is you can actually modify local variables in the scope of the lambda as if we passed by value, or sorry, passed by reference in here. That's where people get a little confused. Like, wow, why would I do that? Or how can I do that? There's a little bit of overlap here. If you decide you want to modify your local variables, you could do it here, or you could do it here. Both are really possible, right? But the key thing, and this is also a piece of the syntax that confuses people, we don't put the type of those variables already exist, right? They already exist in the local scope in which we're defining f. So we just put in the name of the variables and they just get pulled in. There's no need to say anything like this is an int and it's got a default value. It's just going to capture those variables and use them inside of the lambda, which is different than these parameters, of course, right? So we're not creating any new variables, just passing them in. And then there's a little backdoor thing that's pretty darn cool. You can actually put an equal sign in there, and it's going to capture every local variable known to the current scope in which f is defined. That's pretty crazy stuff, because now your implementation here has absolute access to anything that existed and was known in the region of this, or in the scope of that f when we were defining it, okay? And similarly, you can pass them all by reference. So now that lambda can change everything that was in the local scope. That's some pretty crazy power, right? So use those sparingly, I guess you would probably say, okay? So that's the capture, right? So let's take a look at the parameters. Pretty straightforward stuff. It's just the same way you've declared arguments to functions all along. We just give the type and the name, and we know we're going to use that stuff inside of our implementation block over here, right? So we just list those things, and so you could call stuff this way if you want, right? Nothing really surprising there. And all the usual rules apply. Like if you want it to be constant, you have to declare it constant. If you want a reference, you got to give it a reference, that kind of thing. And then, of course, and we're skipping over the return type, we'll come back to that. But the final part here, or the almost final part, is our implementation section. Any code in here is valid, right? But the scope is limited to two things, right? What you put in the capture section and what you have declared as parameters. So it's kind of crazy. Never before have we been able to write a function where we can literally use the straight name that's existed in the scope in which the function was called. But that's what our capture clause gives us. Our implementation can refer to things that existed outside of this scope, and it can refer to them by name, and it can just use them as copies, or if we had a reference up here, it could actually change them as well. So that's some pretty crazy power. It really is. And there are parallels to this in JavaScript and Node.js if you do any server implementation. And some of my worst bugs have come from changing things in my capture clause and thinking they were by reference and they weren't, and I just pulled my hair out to try to figure out what I needed to change. So there's some really amazing power here, and it transcends a lot of languages, but you gotta be careful with it. So in final, then we have our return type, which is int, right? So now lambdas are kind of fluid on this. You don't need to declare a return type in all cases, right? You can specify it to be clear, and I would suggest that you always do, so that you can do something like this, and you'll get an int back. And so the value that we're assigning it to, my int equals function of all this stuff, would match the return type. So no conversion would have to happen in that particular case, because we specified that the return type of the lambda is an int. Now, the annoying thing about the return type, because we've all learned that when we declare a function, we put our return type over here. It's kind of annoying that it's not over there. It makes you wonder why couldn't this be int f, right? Wouldn't that make sense if our lambda had the return type just like all other functions? But you just have to remember it's way over here on the end, right? And so that's probably the confusing part. That's why I saved that one for last, okay? So here in this case, if it was the same lambda we were calling, there'd be a type conversion from into double because we're assigning it to a double at the end, okay? And then here, not to confuse this auto with this auto mystery says, oh, I don't know what mystery is going to be, so I will assign it based on the return type of f. Well, that's okay because f knows what it is. F knows that it's an int, right? But if you didn't do the return type, right, you left it out, it can work in these cases, except for the third case, right? We can't have both of these left and right side of the equal side confused about what type they are, because that's just not going to work, right? So if this is not specified, then you can't get away with auto. So just heads up, that probably is not anything you're going to run into. But so just before I kind of jump into the examples, any questions, syntax or concept at this point? I've been kind of talking for a few minutes. Cool. Okay. Okay, so let's look at a couple examples. So this is the most minimal example we could have of a lambda, right? We have auto return type, or, sorry, not return type. Auto is the name of the lambda. We always declare lambdas of type auto. Sorry, let me restate that. Auto is the type of the lambda that has this name, and it has no capture. There's nothing being captured from the local scope, and it has no parameters that we're passing into the function. It's just going to say hi there. Okay, so that's our hello world function. Okay, and we can just call it like that. And of course, we have to use the parentheses, otherwise it will scream at us because it is a function. Okay, so now let's give it actually a string argument, right? So we can say the name. We could say hi there, so and so, right? So there's the very similar declaration, but we've got some parameters there. This lambda Mickey. Pretty straightforward, okay? Integer, right? So here we're going to pass in a value and we're just going to, let's say, double it. I'm going to return 2 times whatever it was got passed in, okay? And it's going to, it's not a double type, it's just returning twice 2, right? And we haven't declared a return type, so it's going to be interpreted based on what we're assigning it to, okay? Gets really tricky, by the way, and confusing if you don't declare a return type trying to figure out what it's going to convert to. So I always recommend that you do that. But this would print 10, right? Why would it print 10? Because our code has actually incorporated that 2 into the implementation. Okay. So let's try an example. All right, so we're going to do addition and subtraction for you. That was a long dry spell without you guys doing anything, so hopefully people are still awake. We want to develop 2 lambda functions, an add that doubles and returns, adds 2 double type values and returns their sum. Okay, and don't specify the return type in this particular case, just to see what happens. And then subtract, so just another kind of version of the same thing, and return their sum as a double, right? So do specify a double as the return type, okay? So here we're adding 2 doubles and returning without a type, and here we're subtracting and do specify the return type. And then go ahead and test that and print it out and just kind of make sure it works for you. And then we'll talk about that a little bit, okay? I'll set the timer and have a look at the code and see if there are any stumbling points. Just a heads up, I don't know if it's Replit or if my particular solution for this one is having problems. I kind of preloaded a bunch of pages, but if anybody has troubles with Replit, give me a shout out and I'll at least I can adjust how we're going about doing things. Hoping Replit's not dying on us. Okay, yeah, I think it's okay. It came back. I think I just had a bad tab in my Chrome windows. Okay, let's take a look at the solution for that. Pretty straightforward, but we're gonna obviously ramp this up. So I'm just making sure everybody's with us. So there's our auto add, no capture, right? And two doubles, I and J. And then we're just gonna return the I and J, no return value specified in that particular case. And then we'll do this sub, and in this case, we'll actually specify the return type with double. And I didn't put it in parentheses here. You can, you don't have to, it works just fine. But here we've kind of used the auto, remember, it's just, we have to do that when we name our lambdas, right? So in each of these cases, just as we would be writing a function, we're doing it inside of main. That's the strange thing, right? We're just actually doing it right there on the fly. We're creating a named function. That's kind of the new and different thing, right? And then we're going to invoke them down below, okay? So we can add and subtract. So that's what I mean by transient. It's like, okay, well, they kind of only exist in the scope of main. Or if this was some function that you were writing where you're like, I need something that, you know, multiplies two numbers and divides by 1.7, you know, and I have to do it 1,000 times. Do I really need to go write a function somewhere else and put it in a file, or can I just write it right here with a lambda? A lot of times it's really nice to just write it with a lambda and be done with it because you just need it in that one place and nowhere else, right? So we wouldn't do that if we were going to have to rewrite the same lambda in 8 other places. We just make an actual function. But if you just need it right there, it's kind of a one-off function. You can do it just like that, and it works great, right? Okay, so that's our named lambda. It's transient in the sense that it comes and goes in the scope that exists in, right? But we can even be more transient than that, which we'll see in a second, right? So, oh, right, and just one observation, when we don't specify a return value, everything is truncated to an int. And why is that? Let's just go back and look at that. And see if I can't to elaborate on that. Did I jump ahead? Did I jump way ahead? Where am I? Yeah, sorry, I jumped ahead. Sorry about that. Back up. Right, so when we don't specify the type, in this case, it's going to get truncated. So I'm not sure if that is a byproduct. It's a little strange what we're doing here. We're feeding the output of it directly to the cout, right? And so nobody is really specifying the type, right? It's the return type is not specified here. There's no really super clear specification in cout of what type it wants, and yet it does work. So I think that might be a byproduct of cout deciding that if it doesn't know, it's going to treat it like an int. But always better to be safe and specify your type just in case, right? Unless you really know what's going on. So, okay. Okay, any questions before I move on? We're going to move on to the capture example. Okay, cool. Hang in there. I know this is syntax dense, but hopefully you come away with some new tools you can use. So here's our example of capture and the, you know, sort of the realization of what is happening. So Q equals 10, right? And again, think of our functors, our class that we created in our constructor. We said we want our functors to be able to stamp out lots of different functions, right? So sometimes they may have one type of increment, sometimes they may have another. So that's what Q is doing for us here. The value of Q here is 10. So when I define this lambda, it is going to be defined in this moment in time with that value of Q, okay? So the value of Q that exists when we define this lambda gets captured and goes into the definition of this lambda much in the same way as if we were passing it into a constructor of a functor, okay? So now that lambda is specific to whatever that value of Q was when it was captured, okay? So we could say this lambda of 5, and it's going to print 50. Why? Because Q was 50 when I defined this lambda, okay? Now, if I change Q to 100, and there's no, well, it's captured, so it's captured, right? It's not going to change the output. We're still going to get 70 there, right? That's an important distinction that is often lost, and the source of bugs, right? This is one that's tripped me up myself in other languages. So, so that is, in a very simple way, how the capture kind of has an effect. Okay, so we're going to have you incorporate a capture. So we're going to do add mult lambda function. We're going to define a variable before we create the lambda function, give it some value. Okay, and we're going to add that variable to the capture of our add mult lambda function. And then we're going to print out and just call add mult. And you'll see the implementation of add mult. It's sort of a bizarre little lambda function I came up with. But you're going to call it and then go ahead and change or print it out, right? Print out the result of an invocation of add mult. And then change the value of variable and just call add mult again and just confirm to yourself that that particular capture was indeed captured when you created that lambda function, okay? So give that a try and ask me any questions if you have them. Like, once again, I'll set our timer and I'll take a look and see if there's any key points I need to narrate here on this particular one, okay? So I realize this one's probably relatively straightforward. I'm kind of beating you over the head with the meaning of this capture thing, but you probably won't take the full 3 minutes on this, but I'll give folks another minute or two, or another half a minute rather, to kind of wrap this one up. Okay, let's take a look at this one. Pretty straightforward. So there's our Q, of course, captured, right? So we use it inside of the function. And again, the captured stuff, note, we're not saying it's type. and we're actually literally using the exact same name of the variable that was captured. What is so confusing to people is the sheer continuity of the name looks from inside of this function like it's going to capture any kind of updates to Q. And our key point here is that that's not the case, right? So changing of Q is not going to affect it because like our functors that we talked about at the beginning of the lecture, that thing is locked in. It's part of the constructor for that particular lambda that we're creating. And so it's not going to change. And in case my terminology is confusing you, I bring up the functors because there's a lot of parallels, of course, because the compiler is building one behind the scenes for us. But these are called lambdas, and the concept that we saw, used with classes is called functors, right? Okay. Any questions on that? Anybody? Okay. I think captures are the kind of the strangest beast in all of that. It's kind of thing that is really powerful, but sometimes confusing. Okay. All right. So oh yeah, we saw that. Okay. So I think maybe this is out of order. Maybe just a different type of capture. I'm trying to remember where we're going to go with this one. But basically, oh yeah, we've got an argument here that we're passing through. And we can do it by reference. This is where things get really crazy, right? So I can, in my capture, even though the value of it that's passed into the lambda is captured and frozen, if I put a reference in front of the capture, it's actually going to allow the lambda to modify that value at any time if it chooses to, right? So so we could, for example, say double it equals 2 times x, right? We're not returning anything here. We're just changing the value of double it, okay? And we should actually probably return some value here so we don't get a null kind of void return from this lambda. But in this case, we're actually modifying the captured value by reference, okay? So we could just do that. That would work. Yes, it would. Yeah, right. Yeah, sorry. That's the confusing thing, right? So later on, when we invoke this, we pass in the 5, right? And it's going to double it, and it's going to magically, if you will, change double it, even though that double it is nowhere specified in the statement, right? That's a pretty potentially confusing thing, because back here in this definition, we bound it in for reference, and it actually can and does change that value. So that is potentially very confusing, but definitely possible. Question on that? I think we're going to do a little exercise with some references on capture. Okay, let's see. So a couple just caveats here. I think I covered these. It's going to capture the data that we know about, quote, now when we define the lambda, right? It's going to bind it to the call. And so even if it's not around later in scope, it's almost like magic, right? Let's say you call this function later on. If it, potentially in a different scope, it would actually still have it bound there, right? And the arguments that are passed in at the moment of calling, right? So I probably made this one super clear so far, but let me know if you have any questions on it. Okay. Let's see. Homework 9. Okay, so this, for some of you, you do not have to do this, and you don't have to worry if this doesn't make sense. But if you really wanted to do some crazy stuff, you could actually use lambdas to call your worker functions inside of your constructors, right? And one of the reasons for the capture is instead of passing, some of you saw this syntax. I said, don't worry about doing it this way. This was the hard way. But some of you did it this way. Some of you that jumped on homework 9 early, we were passing this in as context to the thread constructor. But we could also use pass into the thread constructor a lambda, which captures this, or in other words, the pointer to the current instance of the maze class that way. So 2 ways to do the same thing. But for the rest of you, don't worry about it. This is the kind of ninja style way of doing it. It's really not necessary. We could do it so much more simpler ways, and that's kind of how I rejiggered homework 9 for you to avoid this mess. But there it is in case you want to study this a little more deeply. Okay. Okay. So let's set up for another exercise. I think we got just one or two more. So for each, you might remember as part of the algorithms library, and this happens a lot in data science kind of stuff. So you want to do something to each member of some container, right? And so for each, its specific syntax requires that you provide at the beginning iterator and the ending iterator, which some of you will recall all of our containers have. And then a third argument for the for each is a function, right? Which can also be a lambda, okay? So we're going to take a look at it first in a generic way without our lambdas to refresh everybody's memory, because this is a useful pattern you should understand. So we have a vector container full of integers, and then we've got some function that does something. Either it prints out an x value, or maybe doubles it or something, but it's not going to return anything. We're going to give it an x, and I think it's just all it can really do is print it out, right? So here's how we would use for each. We'd say for each, vals begin. Remember, all of our containers have a beginning iterator and an ending iterator. That's just how for each wants it. And then we're going to pass in the function name, which is a pointer, right? It's a function pointer. And for each is going to call that function with each item it gets from our iterators and pass it in as x. And then our function will utilize that x value that's passed in to do something like print it out or store it in a database or something, okay? So that's usually where people get confused. It's like, wait, what's getting passed to some function? Well, it's going to be whatever the value is that each of these iterators points to. It's going to get passed in to that function, right? Just one argument, right? It's always one argument. That's what for each does, right? It's going to pick off each one of those things and give it back to us in our function. So if this was with strings, our sum function would need to receive a string type, okay? Notice the similarity in type. Maybe it's super obvious, but so here our vector is full of ints, so our sum function needs to support ints as well, right? Similarly here, if our vector is full of strings, our sum function needs to be able to take strings, because for each is going to feed it whatever is inside of that container, okay? Okay, so that's the model for each. So I'm going to have you do a little very minor tweak on this. So convert the vector type in here to string, and then just pick some words at random and push them into the vector, some strings, okay? So should all be very familiar to you. And then call the for each function using the print me function that I've written for you. I think it's all written for you. And just see if you can use for each to print out each of those individual words, right? You should see those things print out each one that you add to that. So try that, super simple. And then for those of you who are, kind of knock that out really fast, think about how we would go about adding more arguments to print me, because, of course, for each doesn't know or care about anything other than one argument. So how would we modify print me? You could probably guess based on what we've talked about, but try that one first. I'll give you about 2 minutes because I know we're kind of running out of time here. I think this will go quickly. And I think we'll land this one at 7:15 on time, okay? Yeah, so this one's embarrassingly simple. So I think I just kind of wanted to get you warmed up to the for each before I throw the lambda at you, but you should be able to knock this one out pretty quick. Okay, let me summarize that while folks are wrapping up. Pretty straightforward, obviously. Um, so we switch that over to string. We push back our strings, right? So we got 3 words in there. For each vowels, I could have called it words, but vowels, begin, end, print me. No parentheses, of course. And so each of the words will be fed to the print me function, right? And then we just print an extra end there after the for each concludes. So note that our for each parentheses, there's a beginning parenthesis here, of course, and there's a closing parenthesis here. There's a lot of stuff in the middle. It's a little confusing. But we're going to see in a minute. Of course, we know in C++ you can put line breaks between anything. And that's what we're going to do in our next and final iteration of this for today, is we're going to start expanding this print me now to replace it with a lambda, a very transient lambda function that will only exist for the duration of that function call. That's what lambdas are really good at doing. So, but that's our simple sort of reminder on that. No parentheses there. We just pass the name of the function, right? So now with the use of our knowledge on lambdas, including the capture, we can actually build functions right in line there, right? So here's our algorithms. Here are our vector values, right? So now we can say, here's our for each, and notice I've moved the closing parenthesis down there to give me some space. And this is purely for syntax and readability. And this is where I'm going to develop a lambda. And this pattern you will see many, many, many times in many different languages, where this closing parenthesis gets dropped down and a large amount of development happens in here. And man, if you're a newcomer to this kind of syntax and you see this, you think, what is going on there? Like, where does the function for each start and end, right? Because this could be tens of lines in here, right? Where people drop in transient functions either in the form of lambda or something else, right? So we're not going to get that crazy with it, but that's essentially what we're going to do. We're going to call for each, and we're going to build a lambda, a transient lambda right in there as the argument, right? And we know that our lambda is going to get called with one and only one function. But because of all the features that the capture offers us, we can pull in all sorts of contextual information, right? And again, just a reminder there, we're ending with a parenthesis, not a brace, right? It's not the end of a brace for a function. It's just a for each function call, okay? So let's try this. So try using a lambda to write a sum function with for each. So we've got a set of values in a container, and we want you to write a lambda within the for each, right? Within that sort of syntax there, and sum up all the values in the container, okay? I know I've kind of shown you all sorts of syntax, but wind back to a page that has the lambda structure on it, but you hopefully can do that. And then go ahead and print the sum out after the for each finishes. You should get a value of 45, right? So, so basically what you're going to do is you're going to need to pass in sum, right? A variable sum with a reference on it in the capture of the lambda. Okay, so I think maybe that's called out in the code, but I'll kind of narrate over the top of that as you guys work. Okay, so give that a crack. I will kind of just keep my mic on. I'll give you a couple minutes here and see if we can't wrap up by 7:15. Okay. Okay, another half a minute or so. Remember, you will want to pass in the sum into your lambda as a reference because we want to modify that as we sum things up, okay? Oops. Okay, let's take a look at that, see if we can't get you guys out of here. We're almost done. So there's our main, there's our for each, our first for each. We're just gonna, I think, print this stuff out here. Oh, sorry, no, this is what we're doing, our sum. What am I doing? Print the lambda. Oh, okay, right, sorry. There's no capture there, right? We're just printing this one, right? So there's an empty capture statement and we're passing in a double because our container is of type double, right? So the for each is gonna call that lambda. And notice again, we've dropped down that parenthesis down here. It looks like it's the end of a function call, but it's or the end of a function structure, but it's the end of this function call, right? The third argument of this for each is the lambda, right? So that's just printing it out. And then we're going to compute the sum. So we create a sum, right? We set up our similar structure. And here we pass in sum. We capture the sum with a reference, okay? And then we're going to iterate through and just say sum plus equals I. So we're just going to keep accumulating I against that sum. And it just so happens that that's part of the capture. So we can modify that. Now we also could have passed in sum by reference as an argument to the function in good old-fashioned way. That's totally fine as well. In this particular case, the either approach is perfectly fine, as long as we had a reference on the sum, okay? But this is how we would go about, incorporating that in line, if you will, that code in line inside of that particular for each. And it only exists for the scope in which it's needed for that function call, and then it no longer exists. So basically the runtime environment is going to instantiate a functor underneath the surface that carries out this task only for the duration in which that for each function call is being executed, okay? Which is kind of cool. It's very transient, comes and goes. It's nice if you only need a one-time use on it, right? So it's pretty easy to do, okay? And we talked about that closure thing. I think everybody's sort of got that. So I'll leave you with this one thought and then get you out of here. An interesting exercise to do, if you chose to do it, and I will stay around if anybody has any questions on this or any of the homework at any time, is to consider, open and load the files associated, the data values associated with this link here, and then iterate through the container using for each, and compute and print out the following statistics using only the for each and a inline lambda, right? So no named lambdas, just write them once off as you do each statistic. Do the sum, that's an easy one, we just did that. Calculate the average, that's a little more interesting. You might want to pass in more contextual information that you want to modify. Computing the median, that is an interesting one for sure, but a very, very common statistical thing to do with a bunch of data. And probably you want to pre-sort your data values beforehand, but you could probably find a way to do that. Compute the variance, statistical variance. That would be a very common thing to do with one of these lambdas, right? Maybe you just want to do it on the fly, which is pretty straightforward to do. And then if you really want to challenge yourself, try to figure out which of those values in that file are prime numbers using a lambda, right? That's kind of the ninja thing. It's kind of a lambda within a lambda kind of thing, which you'll see if you do it. But you can do it, and you can do it all inside of that function argument, right? So that's it for today. So that is, again, that is the functors, function pointers, the lambdas. And I think there was one other topic we covered, but I'm blanking at the moment. Does anybody have any questions before we say goodbye? Okay, you guys are very quiet today. I'm sure you're ready for the weekend. I hope everybody's doing well. Hang in there. I'll be heads up this weekend on homeworks. Please don't wait till the last minute. Everybody seems to be doing pretty good, and let me know if you need any help at all. I'm around. I'll stay online, and thank you, everybody. Have a good night. Have a good weekend.
Have a good weekend.
Thank you.
Thank you.